Hi everyone. So in today's thermo lesson, which this is going to be lesson number 4, I'm going to split up today's topic into 2 videos to separate like the concept in one video and the math in another video. So this is going to be part number 1. And we're going to talk about calorimetry. So we've been talking about heat, which we know from yesterday's lesson is represented by the letter Q, and we can use Q equals M times C times delta T in order to calculate that. And calorimetry is the experiment where we actually get that data. So it's a lab experiment, which I can't remember if I put this in your vocabulary words, but if I didn't, you should add it. So it's a lab experiment that is used to determine the heat, not to determine the heat, it's used to determine the specific heat capacity of unknown chemicals. It's like a way to figure that out, or if you have like an unknown metal, or it can be used to calculate the enthalpy, which is represented by delta H, of a reaction. And enthalpy, which we'll kind of get into down here, enthalpy delta H of our reaction is, it actually measures the total amount of energy, so heat plus work, of a reaction. So we know that when some things happen, like for example, if a Cheeto burns on fire, not only does it produce heat, but the mass also like shrinks and it gets closer together. So that would be heat and work combined. But most of the time we just focus in high school chemistry on the heat portion. And so what I've put here is I've just added some images of what this would look like in the lab. So this type of diagram here would be called a coffee cup calorimeter, because we would use it, we would make the calorimeter based out of 2 styrofoam cups that would be just kind of like nested together or sitting in one another. And you would put a cork stopper as like a lid. You would have a stir in order to stir your reaction around, and you would have your thermometer to measure the temperature, and you would have your reaction. So for example, you would use this and you would say, okay, if the water was originally 25 degrees Celsius, right, and then you add the reaction, you can see that if the temperature were to decrease, that means that it's going to be endothermic, right? It's absorbing the heat. That reaction is absorbing the heat from the water, so the temperature of the water is going down. But if the temperature of the water were to go up when you add those chemicals in there, then you would know it's exothermic. It's releasing heat into the water, which is causing the temperature to go up. We can also use this for like food and other items. So for example, again, if we were in class, I'm so bummed that we don't get to do this. We would be doing actually both of these experiments. We like to light a Cheeto on fire. Is particularly fun, one of the puffy ones. And what you do is you take an aluminum can, like a Coke can, and you fill it with water. And you find out, okay, let's say we know that this is 50 grams of water and it's at 25 degrees Celsius. Well, what we do is we measure the temperature. So we would put like a thermometer in here, and we would measure the temperature as when we light the Cheeto on fire, because we know that the Cheeto has energy in it. We eat food in order to get energy. And so we light it on fire and as it burns, it releases the energy inside of that Cheeto, and the water is absorbing the heat. So the temperature is going to go up. And so the highest temperature it reaches would be our final temperature, and we can kind of use our Q equals M times C times delta T formula to help us figure out how much energy is released by the Cheeto. Now, this diagram here, this one's a little fancier, and we wouldn't use this kind. This is called a bomb calorimeter, and the reason why it's called a bomb calorimeter is because of this portion right here. That's the bomb. This is how scientists figure out exactly how many calories are in your Doritos or in your taquitos. What are those things that your Takis? Your Takis, those are the things you guys like to eat. Basically, they would put a tacky in this little cup here, and there's oxygen in the atmosphere, and so these ignition wires basically would create a spark that in the presence of all that oxygen would literally set off like a little food bomb inside your picture. Not inside your picture, sorry. Inside this picture, because that's what we're looking at, but actually inside the device. And as it kind of explodes and releases all that heat, again, the water is going to absorb the heat that's released. So even though we can't measure the heat directly in the fire, we can measure it indirectly through the water that surrounds it. So calorimetry is an indirect way of measuring energy. And it's basically this idea. So here, this would be an example of if you have an unknown metal. Let's say M is our metal, and we don't know what it is, but we do know that, let's say over here, we heat up M in a thing of water to 100 degrees Celsius, okay? And then we take that metal and we put it in the water. Well, if the water was originally this many degrees, let's say again 25 degrees Celsius, because that's about room temperature, okay? Well, if the metal was originally 100 degrees Celsius, what's going to happen is the metal is going to experience an exothermic reaction. It's going to release heat, which you can see as these arrows with Q going out. It's going to release heat, whereas the water, which is our surroundings, is going to be endothermic. It's going to be absorbing the heat that the system is releasing. And so what we'll see, which is we see in this picture here, is that the thermometer has gone up. So now we know the temperature of the water has risen. Maybe this is 30 degrees Celsius. And we know that that's not a big change, but we know that the specific heat of water, so C of water, is equal to 4.184 joules per grams degrees Celsius. So even though the metal is initially at 100 degrees and we add it in, and that's like really hot compared to 25 degrees Celsius, okay, it's not going to change the water's temperature by that same amount simply because it does not, it takes a lot more energy than that to move water's temperature by 1 degree, whereas metal has a very low specific heat, so it's kind of different in that way. So these are kind of the diagrams, and again, these first two are kind of the ones that you really need to focus on, and this last one, the bomb calorimeter, is kind of just for funsies, but this last one, we're going to do problems that describe this process and also these processes, which you could do the metal one in here. This is kind of actually the setup we would probably use for the metal. We would put our block of metal inside this coffee cup, and we would know exactly how much water there is and the temperature of the metal and whatnot. So a key thing to kind of keep in mind as we're doing these problems is that specific heat is going to be unique for all the compounds, okay? It's unique, and it can be used to identify unknown metals, okay? So if I have just a random silver metal, this is an experiment I can do because silver and steel and aluminum and all these kind of silver metals that exist in the world all have a different specific heat and can be separated out that way. And then that, again, enthalpy, which we mentioned earlier, which we're not going to talk about a lot in this video or in the next one. We're actually going to talk about enthalpy next Monday in our lesson on that day, so in a couple of lessons. But with calorimetry, there are going to be two basic assumptions. One of them is that the heat absorbed by the water is equal to the heat released by our substance, whether it's the piece of metal or it's the reaction. The heat absorbed by the water is equal to the heat released by the substance. That it's exactly the same. Now, in reality, it's not actually exactly the same. Some of the heat might not actually get released, or some of it might be absorbed by something other than the water, and so it might not be that way. But for our calculations, we assume that they are equal. Excuse me, I'm feeling a little tired. But we know that the symbol for heat is Q. So what we're saying in symbolic terms is that Q of water, which is positive because it's being absorbed, right? So it's gaining energy, is equal to the heat, or Q, of our, let's just call it our metal. But since it's being released, that means that energy is negative. And so that kind of leads into our second assumption, which is just like a further clarification of that, is that only the water is absorbing, only the water absorbs the heat released, and that no energy is lost to the surroundings. And the way that this might play into effect is, for example, if we look at this one with the food, if we look at this Cheeto, we know that the heat, this fire, is going into the can and into the water, right? So in reality, we know that the air around the Cheeto is absorbing some of the heat. We know that the actual can itself is absorbing the heat, and we know that the water inside the can is absorbing some of the heat. However, in our experiments, we make the assumption that no energy is absorbed by the air or by the can, that it is just by the water. So in reality, we know that our calculations are going to be off by just a little bit, which is why this is kind of like a high school experiment setup. In this kind of bomb calorimetry, more like industry, what you would use in research, they're going to have a lot less room for error in terms of that. But this is one of our basic assumptions for a simple calorimetry experiment. And so this is kind of like the concept of calorimetry. And so in part 2, we're going to look at 2 examples on the kind of calculations that would go with this experiment.